Hello everyone, it's March 20th. Alright, so the goal today, first we want to finish the challenge and then I want to look at the last contest problem from yesterday. It was pretty hard. I tried to give it a bit more thought, but still I had no where to go. But that problem, again, if you take a look, it has lots of hint. So maybe we can build something up by just looking at the hint. Alright, so let's first go to today's problem called partition labels. We solved last time in September. Okay, so given a string S, we want to partition the string into as many parts as possible so that each letter appears in at most one part. Note that the partition is done so that after concatenating all the parts in order, the resulting string should be S. Return a list of integers representing the size of each part. So we try to partition into as many parts as possible so that each letter appears in at most one part. So each letter has to appear in at most one part. What does that mean? Each letter appears in at most one part. So a letter does not appear in two parts. So for example, in this case, if we don't partition this way, we do ABA, right? And then we do BCBA, and then B appears in two parts. So which means either a letter doesn't appear in a part, or a letter has to appear if it is in it. So this just means I want the letter to appear in only one part. So if a letter, let's say A, appears, A has to appear in the first part, right? A has to appear in the first part. So, which means all the A's has to appear in the first part. So what we can do, we can grab the indices of A. We find the largest indice of A. Well, actually, the starting and the end of A. So for this one, we're starting with A, and we have to find the A, right? So we find the A. So that is absolutely necessary to be one partition. But then, so we have this range. Then we look at B, right? And B, it's within this range, so B is good. And C within this range is also good. And nothing, right? That's it. So we walk through this thing, and that's it. So that's the first partition. Now we look at D, right? D, we have to at least get to this, right? That's the end. Now look at E. Oops, E is larger, so we have to expand. Now we have this. Now F is unique. E, we have it. G is unique. D, it doesn't have anymore. So that's the second partition. And the last partition, H, is by itself. So that's the start, right? That is the start. Oh no, hold on. That's not a start. H, I didn't see that. That's the start. Now I, we have to expand to here, and J, we have to expand to here, right? And for this, the length, so E, we go here, C, we go here. That's it. Okay, so that is the solution. That's how I'm going to do this. Let's see if we can do it efficiently. What do you mean? So what we need is the last index, right? We want the last index of each letter. Therefore, what we need is just a hash map. That's all we need. So we're gonna go through the entire thing and create a hash. Actually, do we even need a hash map? The lower English letters. Yeah, I like to use hash map. So we use hash map, right? And then we should say for I letter enumerate as basically hash map letter equals I, which I just realized we can do better. We do this I, right? So that's hash map, and then rest equal to this, right? And we always have a start, right? So start will always be 0, right? And now we just say for let's say for letter in S, right? We'll go there, everyone. And for each one, we'll look for, so start and end, right? So start equals end equals 0. And then for letter in S, right? So for letter in S, we say if let's say if hash map letters last is equal to end, right? So if it's equal to end, no, that's not true. If I in the numerators, if I is equal to end, right? Which means we walk to the end, and if we keep going, it has this new one. So if I equals end, then rest dot append end minus start plus 1. That's the total number. And after that, start will equal to so start will equal to end equal to I plus 1. Right? So if I equals to else, then I will be smaller than end. Right? I will be smaller than end. So I is smaller than end, or basically say end will equal to the maximum of end and hash map letter. Right? So try to expand. And yeah, so let's say the end situation. I will equal to n, we'll do this. Yeah, so that's return rest. Let's see. We have this. Need to 98. So 978. This is 10. I'll throw in a few more. Right, like if it's A by itself, that will be 1. Right? What else can you think of? What if I have repeats? Yeah, repeats, then let's say AAA, it should be 3. Right? If we do AAAB, that shall be 3, 1. Of course, if we do BAA, that should be 1, 3. Just some test cases. Partition S. Ew, the heck? That was absolutely not right. Hold on. I equal I is. How'd you solve that? And so n has to hold on. Maybe we can, yeah, let's change this. Let's say for I in range 1 to learn S. Okay, so start should be 0, right? And shall be hash map S0. Start and end. And now we go from 1 right? And the first one, so if I is larger than n, that means we have, if I larger than n, then we do this. After we do this, I is larger than n. After we do this, start and end shall equal to I, hash map si. Yep. Else, if I not, then we're going to try to expand on I. So like this. Okay, so we need to do one more at the end. So append and minus start plus 1. Yeah, because at the end, I is larger than, I is not larger than n. I is equal to n. So the last one is never fulfilled. Yeah, this one shall be right. Let's run it. Oh, we actually run a test case. Something like that. Yep, I think it's good. Okay. 39, it's pretty good. Let's just take a look at this one. One solution. So first find the last index of each letter, and then we create a window that covers the first and last appearance, of S0. We then iterate through each letter, and if a letter's last index is larger than the current window, the window's and is expanded. This stops when current index is larger than the window. That means all the letters within the window only appears in the window. Thus, the size of the window can be pushed to the result list. Okay, so we run in 39, 92% ranking, which is ON. This is ON solution. All right, I'll just take a look. So it ranges. So I'll get a range. I'll get a partition. Oh, we saw the range. It is merging. That's true. It is merging. We merge these, so we sort it, right? We sort it, and then if I have partitions, we get the last one. And if PE is larger than S, then partitions 1 equals the maximum of yes. Otherwise, if PE is smaller than the current start, then we add a new one. Yep, it's the same idea, but this one's a little bit easier. I'm also merging. I'm finding the partitions, but in a more implicit, right? More implicit way. Okay, so we're done with this. All right, now it's time to. So the problem with this is I was trying to think maybe I can build. Well, here's what I thought. Right, I can have every letter. I can note the length of consecutives, right? So this one will be 1, this will be 1, this will be 1, this will be 1, this will be 2, this will be 1, so consecutive to the right. So once one of the letters get changed, like this one get changed into a B, and I look to the left, right? Then I look to the left. Actually, look to the left is not working, right? Yeah, like I push this in, then everything on the right doesn't have to change, but everything on the left will have to update, right? Because I add a 1, right? I basically add a 1. So this value will be 1 plus whatever here, but everybody else has to, this is a plus 1, everything has to have to plus 1. So that will come up with like maybe O n squared. So that's not working. Now, like, can I just count? Because the query process can be done in OK, right? I mean, like O1 time, I can change it into B. But after changing to B, how do I get a maximum consecutive length? That's the problem. That's where I need to check. Hint. Oh my god. It is segment tree. I was trying to avoid segment tree. I don't like segment tree. Yeah, it is a range query. Okay, so how does segment tree need to be built? So the segment tree can be built over the entire thing, right? Which just means, let's say what we want is giving me a range. I want to find a maximum consecutive overall? The maximum consecutive overall? Is that what it is? Let's say we'll build a segment tree on this, right? So we have segment tree is we given a range. This range, let's say 0 to 0, 1, 2, 0, 1, 2, 3, 4, 5. So 0 to 5, I want to build it, right? And we don't know, so we split it. and to the left half and to the right half. Then we're going to find the left on the left, the maximum on the left and the maximum on the right. Okay, so on the left it will be 0, 1, 2, on the right it will be 3, 4, 5. 0, 1, 2, we keep splitting, and we will split on this. On the left, that's so this 0, 0, right? 0, 0, 1, 2, and then 1, 1, and then 2, 2. So every term will be 1. So when we merge, we find the maximum on the left, the maximum on the right, and then we need to find the crossing. Yeah, the crossing. So the crossing, we just, if the two are not the same, then the crossing is 0, right? There's no crossing. If they are the same, then we need to know how much is this and how much is that, right? That's what we want. How do we know that? Well, we can read it through. Hold on. So what we could say is 0 to 5, right? And we don't know what's this level, so we break it down that this level will be 0 to 2, 3 to 5, 0, 0, 1 to 2, 3, 4 to 5, 1, 2, 4, 5. So 1, I want to know the maximum of this is just 1, right? Which is B1. This is 1. 2 is also 1. 0 is also 1. Okay, 1, 1 come back to 1, 2. So 1, 2, left is 1, right is 1. Crossing is 0, so that's also 1. Come back to 0, 2, right? So 0, 2, left is 1, right is 1. Crossing is also nothing, so that's also 1 on the right side. 4, 5. 4 is 1, 5 is 1. Come together, 4, 5 is the same, so we expand, and now we see the maximum is 2, so 4, 5 is 2. 3, 0, 1, 2, 3. 3 is just 1 by itself. So now we have 3, 5. 3 to 5, 3 is 1. Left is 1, right is 2. Crossing is nothing, so that's 2. And the left and right, 1 and 2. So overall, it's going to be 2. So that is the starting point. That's my segment tree, right? So now I say I change the position on indices 1. So we come in 1, go to left tree. 1, go to right tree, right? 1, go to left tree again. So this one I change into a B. Okay, so now this one changing into a B. It doesn't matter, it's still 1. So coming back, now we merge. Oh, that become 2. You gotta be kidding me. And this becomes 3. So, oh, what's the runtime on this? Maximum on the left and maximum on the right. And a crossing. We should record the crossing as well. Yeah, we should record on two values. We need to record the crossing as well. So if we record the crossing, when we merge, right? When we merge, hold on. How do you mean by crossing? So for me, if I split into two, right? So for me, because I am, let's say a left, I'm a right segment, so I need to go the left. So I calculate how much is going from the left to the end, right? And then I split up, right? I split up. And then when I split up, so I have these and these coming back, right? They coming back. I want to calculate a crossing, so I need to know this and this. Okay, so let's say I have that. So I combine, I have this. And then I look to the front, right? I look to the front. See if it has been changed. So it's changed. So in this one, it will change. What if at each one I produce three values? The leftmost, so go from the left, go from the right, and the maximum. So I have three values. Okay, and then when I merge, right? When I merge, so I can use these to calculate the crossing, and I have the maximum this, so I have the maximum. And the right will be the same as this. The left will be same as this, unless the crossing merge them together. Right? Yeah, if you think about it, right? So for each segment, I have the left, I have the right, and I have the maximum. So I have three values. So I merge. So the left and the right also has to have a letter attached to it. Well, not necessarily, right? Not necessarily, because if I have two values, that means the left and right must not be the same. Oh, it could be the same. It could be something in the middle, split them up, right? And then we merge together. If we merge together, I do need a letter. So we merge together. Yeah, if it's split up, then if we merge together, it will remain split up, right? It will remain split up. So if I have a left, if I have a right, and then we merge, and then we have left, right, then just merge the middle. Right, we just merge the middle, it doesn't matter, and then we have the left and right, it's the same as the left and right. But if I have, let's say on the right is a none, right? It could happen if it's a none, so we don't have a go right. Ooh, we don't have a going right. We actually do have going right. How do I represent this? I always say if the right is nothing, right, is a none, then that's the entire thing is the same value. So I just look to the left, and if we can merge that, I make change. That might work. Hold on. I think I still have it open. Oh, actually I don't. I was so frustrated I didn't even open it. Segment tree, and it's delicate, but I actually do believe we can solve this. Oh, this is the Dijkstra one. So I do believe we can solve this. So what we want to do is create a segment tree. So we need to create a tree first, right? And then every time, so we'll create a tree, and every time we will update the tree. Yeah, we go to the J, and then bubble up. Again, update the tree, update the tree, update the tree, every time I update the tree. So we need to first create a tree. Maybe I can create something called a segment tree. Right, we create a tree which passing in a list, and then self.tree equals a node, and the node is going to be a list. Right, we turn the node into a list, and we have the first two values, the second two values. So the first will be two values. We have the letter and the letter and a value, left to right, letter and value, right to left, and the maximum. Right, and the maximum we just need a number. We don't need to know which one, right? And with that in mind, so I have all these three. Okay, so let's say class segment tree. Oh, this will be interesting. S. Right, and then we say self dot list equals list s, and self dot head, not head root, equals self dot build. Right, let me say self dot n equals len s. Okay, so now in the def build, how do we build? So build, actually maybe I should just say self.build, self.root. So we build root, so we start with this, right? And this represents, which is fine, we know what the node represents, and I'm going to build this. So the build is just a node, right? What else? Well, we actually need to have three values. Right, I have three values. Actually, let's make it so this is going to be this and a value. This is also this and a value. So I'm going to build this, and we need to have left and right. Alright, so we have L and R. L is int, R is also int. node, let's just make that into a list. So that's going to be 0 and self.n minus 1. So that's the root. Root is represented by this. So we're going to build this, right? How do we build this? Well, we say if L is equal to R, then... Oh, I just realized. Yeah, we do need a node. Tree node. We don't need to know the range within this node, right? All we need to know the node. What do we need to know about the node? Well, we need to know about the node. I don't think you need to know about anything of the node. Well, you don't pass anything to it. I'll go left and right, right? So come back in this level, then we will handle stuff. Yeah, I don't think we need to do anything. So what we need to save is self dot left continuous, which are equal to, say, initially I don't know, right? I just initialize to count and then self dot right r count and L continuous, R continuous. So it's also this, right? And then we also want self dot max continuous equals 0, and self dot left equals none, self dot right equals none. Yeah, that's the starting point. And then root is just going to be a tree node, right? Now I think self.build shall return a tree node. Self.build, taking the left and right and then return a tree node. How about that? So if L is equal to R, then we're going to return let's just say node will equal to a tree node, right? And then we'll say node.L continuous will equal to self.list L and 1. R continuous will equal to self.list L. Oh, list R doesn't matter, it's the same. That's going to be 1. Self.max, not self.max, or node.max count equal to 1. And then return node, right? That's when L equals R. Otherwise, L is not equal to R. If it's not equal to R, then I have, let's say, L child and right child will equal to self.build L plus R divided by 2, right? L plus R divided by 2, and self.build, this is L plus R divided by 2 plus 1 to R, right? Like it's, say L is 1, R is 2, it'll be 1 on here, it'll be 2 on the other side, yeah. So that's, we have a left child and right child. Now we have both child, right? We have both child. So now what we need to do is for the left child on the right content and the right child on the left content. So we can compute. So left child, right? And node equals tree node. This can go on here, so it'll be the same, right? We can actually say node dot left, because these won't change. Node dot right. Okay, node dot left, node dot right. So we'll grab this. Now we grab this. Then what? Then we need to first compute the maximum, right? How do we compute the maximum? We say cross. Right, cross are equal to 0 if node dot left dot right continuous 0 is not equal to node dot right dot left continuous 0. Right? The right is not the same. Else is the same, then that should be node dot left dot right continuous 1 plus node dot right dot left continuous 1. So that's the crossing. So node dot max shall equal to the maximum of cross node dot left dot max and node dot right dot max. Okay, so this we handle the left to right, handle the max count. I'll just call it max. Oh, okay, max continuous. Okay, so we get a node max continuous. But left to right, so we just need to find the left and right count continuous for the node. Now, how do we find that? Now we find that by checking, right? If, because it's the thing is, because in this case, left and right, I produce the same value. Okay, I produce the same value, which is not correct. This is actually not correct. You think about it, right? It's not correct. I shall have only one. We can, I don't know, arbitrarily choose. Arbitrarily choose left and the right, coming from right will be empty, right? Yeah, just arbitrarily choose this. So we only have the left. Right is empty. So now I have no left and right, and a cross. Now the cross will be interesting. What I say is if these two do not match, right? These two do not match, but it depends. It depends because, it depends. If the right is the empty, right? Then we need to compare to the left. Right? We need to compare to the left. If not, then it's fine. Okay, so here is the deal, right? We're gonna say if node dot left dot r continues 0 is if it has something, right? If it has something, then we say cross is equal to 0 if this is not equal to this, else and then be this plus this. So we have nothing to do with the front because that's how it's designed. Else, if it is, then cross, right, well, still equal to 0 if node.left left count 0 is not equal to node.right left count 0. Else will be also add them together, or we add some other values, will be the left count. All right, so that's the crossing. So now we have the max crossing. And finally is to compute first the left, first, and right, right? So we say, right, if, again, if node or right count exists, right, if this one exists, then we can guarantee that node.left continuous will equal to node.left continuous, right? And node.right continuous will equal to node.right continuous. So because the right continuous is always the same, it will not change. It will not change. Else, if node.left or right continuous is empty, which means the entire thing is the same thing, right? It's the same thing. And now we need to consider, right? Now we need to consider. Then we need to say elif node.left continuous 0, right? If that thing is not equal to node.right left continuous 0. So these, so the left is completely occupied, and on the right side we pick the left, right? And if these two is not the same, then we do this thing again, right? So if they're not the same, so it's the entire thing on the left and it's a different thing on here. So now we do the same. Else, if they are the same, so the left's entire thing is equal to on the right side the first entire thing, then node.left continuous shall equal to something. What is this thing? This thing will be node.left continuous 0, and the length is going to be this plus this, right? There's going to be this plus this, and the right is still the same. Therefore, what we find out is the right will always be the same. The right is always the same, and the left depends, which is if it has a value, right? The right has a value, or the right does not have a value. So either this or, that's fine. Either this or the left and the other things left, these two left are not the same, right? In this case, then we just say the left equals the left, right? Else the left will equal to, which means what is else? Is this or this? So it's empty, and they're the same. So now we need to put them together, and our right is still the same. And after we've done this, we return node. Okay, so that's build. So now we build a tree, right? Now we build a tree. Now after we build a tree, we need to update. So def update. Now what is update? Update is self we need to change the index, right? And changed what is update. Now update is, we're gonna go through the whole thing. Oh, update, and then also we need what do we need on update? We also need a left and right. So left and then right. This is the index. Probably should do li. Yeah. You know what? I think. That's fine. Let's do this. So much to change. All right. So how do we update? So we say mid equal to L plus R. Oh, actually, I don't need to do this. Right. So after update, finish calling. Yeah, so if L plus R divided by 2, that's the midpoint, which here I think I got it wrong. I should throw the midpoint to the right. Hold up. I say mid equals L plus R divided by 2, right? And I want to throw the midpoint to the right side, so I want a mid minus 1 in this one, and this is just mid. So I say if index larger or equal to mid, right? If it's larger or equal to mid, then we call self.update. Still index, new letter. Now we need to do a mid. All right, and then this will be mid, and then this is a mid and R. Else self.update. Index, new letter, left, and the mid minus 1. Right? So, first, if index is equal to L, equal to R, we're going to go all the way down to the leaf level, right? If the 3 are the same, then what we do is we'll update. So self.list index will equal to new letter, right? And hey, what about a node? I need a node, tree node. All right, so if this, I can update this value. And then what? And then I say node dot L continuous and 0 will equal to new letter. Node dot right. There's no right continuous. Max count doesn't change. So that's it. And then return. Right? Otherwise, we do the mid. If we do larger than, then we say we're gonna go node dot right. Otherwise, we go node dot left. Okay. So once we handle this, once we update everything, now coming back to me, right? Now it comes back to me. Now when you come back to me, what do? When I come back to me, I need to check the left and check the right, right? So yeah, so my left, it's all depends, right? For me, everything is depending on my left child and my right child. So basically, isn't that the same thing? I think it's the same thing. I'm gonna call it merge, right? Def merge. So we have a node. Now I'm gonna merge its left and right. Doesn't return anything, right? So I'm gonna merge its left and right. So I'm gonna take all of this, put it here. Merge left, right, child, children, child. So I'm gonna merge left and right child for the node. And we say left child, and we crossing, right child, blah blah blah. Once we're done, so here we just call self dot merge left right child of node, and after update, call the same thing and return. Right. So this is the second tree I have built. Now solve this problem. So first of all, we're going to call it self on the root equals segment tree. Actually, we're going to call it tree. Tree equals segment tree. We're going to pass an s, so we pass s, right? And then we say for character and the index in zip query characters and a query index, right? What? Character and index. Now we're going to do tree.update. Right, when update, we need a node first. So that's tree.root, that's the node. And the index is just this index. New character is this. Left will be 0, right will be len as -1. But actually, did you even use this? How many times did you use self.n? That's it? Waste. Yeah, len is -1. Left, right, right? So we update. And after update, we're going to say res equals this, right? After update, res.append tree dot root dot tree dot root dot max continuous, and then we return res at the end. All right, let's see. We have this 334. All right, if it's not right, I'm going to go to bed. 2, 3. Okay. Huh. All right, so we have S, query characters, query indices. S, query characters, query indices. Maximum depth. Build. How? Let me think. We have 1, 2, right? It was a 3, 3 divided by 2 is 1. So mid is 1. Oh, shoot. Mid is 1. I think that was earlier I got confused. I don't know what I was doing there. Alright, so this is the mid. So if it's larger than mid, then we go to mid plus 1. Otherwise we do this. No attribute max. Where? Of course doesn't have. It's max continuous. I'll say 0 if there's an else. Oh, here. It's 1 on 1. Okay. Let's see. So this entire process is O1. Everything is O1. So this will run. Build it is log k. Alright? This one is log k. So build takes log k. And the merge is O1. So build is log k. Update is log k. So that'll be OK log k. Huh. a wrong answer. I do believe I'm on the right track. Expected is this. All right, let's take a look. What I got is 1. Oh, the second one is wrong already. Okay, so we have 0, 1, 2, 3, 4, 5, 6. So 0 to 6. Right, so 3. 0 to 3. 4 to 6. 1 to 0 to 1. 2 to 3. 0, 1, 2 to 3. 4 to 5. 6, 4, and 5. Okay. So there's a lot of moving parts. So the 0, what we have is 0, right? So the 0 we have is G, 1, and then nothing, 0, the maximum 1. Now 1 is going to be E, 1, nothing, 0, and 1. So 0, 1, it will be, oh, it's too small. Can't even write it out. G, 1 is on the left. On the right, on the right is not correct. On the right is not E. It's not empty. Ooh. Let me think. Now I have to redo this. Oh wait, hold on. It's okay. Wait, is it okay? No, it's not okay. It's on the right. It shall be E. Which means if I'm on the right side, I shall have shall be this. Right? Then how do we know? Well, I know the length. Make some changes. Alright, so we'll have to do this. Doesn't matter, it's the same, right? Mid, and then we're gonna merge. Now, this merge takes a little bit more work. How does it work? I will have to say, so there are multiple situations. If the left is the entire thing, the right is not the entire thing, right? So if left is entire thing, right is entire thing. Left is not, right is not. Left is, right is not. Left is not, right is. So these are the situations. So we're gonna just do it this way. Okay, so if left is the entire thing, how do we know the left is the entire thing? Well, we know that by knowing the left child's range. So what we need to know is the current. So we need L and R, right? So we produce the mid. Oh, okay, I'm probably just do mid as well. Alright, I got it. Oh, but actually what I need to know is just the total range of the left and total range of the right. So we can just say, let's say L range, right, and R range. Okay. So now what we just say is left is left is left all is all the same, and right all the same. All right, that's the first condition. And the left all the same, right not all the same. And then left not all the same, right all the same, and left not all the same, right not all the same. These are the conditions. So go back to left all the same. How do we check if left all the same? We say if node the left count 0 is equal to node left right count 0 and node left dot l count 1 plus node left r count 1 is equal to, this is the left count and right count. Ooh, hold on, that's not true. That's not true. No, they will be the same. Equal to this and equal to left range. Right? So maybe we can just do this. This is left all the same. L all same is L all same equal to this. Right? And then we can produce, let's say, is R all same. So on the left will turn into right. Right? The right left count, right continuous, and it is the same and equal to right range. Right? And then we just say if is left all same and is right all same. If the left same and the right all same, well, all same, then right, there's a cross equal to 0 if no dot left dot, oh, it's all the same, so it doesn't matter. So this one, okay, we can do this. Right? If the left my count is not equal to this, then it'll be 0. Else it will be right count plus right. Yeah, that's fine. This is all the same, right? So that would be the crossing. So we get a crossing. Then we can do this. This I can do at the end. So we get a crossing, but the left and right needs to be rewritten. So they're all the same. So no dot left count shall equal to you know what? I think we should separate out. So if they are not the same, right? So if the left and the right, they're not the same, then we do cross equal to 0 and node.left count will equal to node.left.l count. Node.right count equals node.right.right count. Done. Else, if they are all the same, then cross basically is equal to the sum of them, right? And node.left count will equal to a node.left.l count 0 and cross, because that's actually the entire thing. And node.right count will equal to node.left. Actually, I don't like it. I like to do it again so they don't point into each other. They should not point into each other. Each one should be a new thing. Yeah. Each one should be a new thing. I can just say it's right. Right. Right and a right count. Okay, so that's that. Okay, elif is left and not is right. Okay, so left is full, right is not, right? In that case, if node left or right is not equal to node right dot left, then cross is 0, and node left equals this. Copy it. Node left equals left, and node right equals right. That's true. Otherwise, if they are the same, then cross equals node left or right, node right dot left. That's true. And left will equal to node left cross. Yes, because it is cross. It is cross. And node right shall equal to node right. Yeah, that's different. So we're basically gonna copy this thing but make this slight change. So this is fine, but this shall equal to this. Because the right is not all same. Okay. Okay, elif not is left all same and is right all same. So I'm pretty sure we can copy this, just make slight change. So left is not all same, the right is all same. And as again, we compare right continuous, and if it's not the same, and then the left continuous, the right continuous, that's fine. This is all fine. This is all fine. So if it's the same, then we can say left to right plus right dot left. That's also fine. And this is not fine. This is going to be, because the left is not the same, so we have to do this. And right continuous will be node. Should I just copy this one? Right. Okay, so that's that. And then last one else, which is left is not all the same, right is not all the same, right? So in this case, I'm pretty sure we'll copy and paste majority, which is if left equals left, that's fine. Otherwise, left or right, right or left, that's fine. And left continue. So we are basically going to do back to this one. So if we take a look, this is exactly the same as this. Oh, actually, no, it's not exactly the same one. I'm realizing something. Like these are the same. Therefore, don't have to do this. We just handle the cross. This is this, right? So this is all different. And this one, the right is the same, which means we don't have to put it in here. Put it right outside, right? And this one left is all the same, so which means we don't have to put it there. The left can come outside. So that is merge. Okay? So when we merge, no, we need to know the left range and the right range. So left range, the total number on the left, right? That should be the mid minus left plus 1. And the right range. So we know the right range should be r minus mid minus 1 plus 1. So that's the r range. In this case, node is the same thing. Oh, forgot one more thing. Max count. There's a maximum. Node dot left dot max count. Right dot max count. And cross. Okay. Right. So pass. Oh. 222. How? There's a situation I didn't consider. It says the count is the same. No, the count is the same. And then it's equal to left range. Left continuous, right continuous, right? So they have to be right continuous, so they have to be the same. And this side is equal to this size, and the size has to equal to left range. So is left all the same, right all the same? So the right and the right and the left, if they are not the same, then I don't have crossing, that's true. And then the left equal to this, the left, the right equals to not all right, continuous. Otherwise, the crossing will equal to left or right continuous plus right, not all right, the left continuous. Okay, and this will be the cross because it spaces the entire thing. Left is all the same. I don't know. Need to investigate this. So LR node left, no L continuous, right continuous, and node on max. Okay, let's see. So we have 0, 0, 1. Oh, I didn't count this one. So let me try this one too. I'll go to else. Mm-hmm. 0, 0, 1, 1, then 0, 1. Mm-hmm. 2, 2. Mm-hmm. 0, 0, 2. AY, yeah. 3, 3. 4, 4. 3, 4. 0, 4. That's correct. Okay, so this is right. So it's update. Update probably has issue. Update the left, update the right. Alright, this is update. So update, first one I update A at position 2, so 0, 1, 2. Alright, so update, so we go to 0, 1, 2, 2, 2, right? That's the first one. F is equal to 2, and ooh, I forgot this. Right continues to 0. Oh shoot. Yep. This shall be right. Okay. No. Come on. How? Oh God. Okay, log K is not good enough? Oh, I thought we got this. Alright, try it again tomorrow. Alright, I'll see you guys tomorrow. Adios.